you very much, and I really appreciate the invitation to talk at a distance to you. I really wish this was in person. In fact, unfortunately, I've got to end promptly at 10 o'clock because I have to dash into Ottawa to give a seminar at Ottawa University, and I much prefer in-person presentations. But here we are. So, as Wesley said, I've been in Magnetotellurics for quite a while, 51 years. And so when you do something for that long, you learn a bit about it.
Sorry, I backed the buttons. That was my fault. Alan, I muted you.
You might want to save that till later.
Keep going.
I am, as Wesley said, I'm the most published and most cited scientist in magnetotellurics. That doesn't necessarily mean all that much. It just means that a lot of people cite my papers. But anyway, before I get into the talk, just a couple of announcements. The first is, what I'm going to try and give you in the next 45 minutes is a précis of a 2-day short course that I give. And this is a short course, a lecture-based short course on magnetotellurics. And coincidentally, I'm right in the middle of presenting this short course to an industry client. And we're doing it over 2 weeks, 4 morning sessions over 2 weeks. But I was just talking to Stephanie, hopefully might be able to arrange to give the short course prior to SAGA next year. So anyone interested, please contact me. Another announcement is that the electromagnetic induction community, the mostly academic electromagnetic induction community, we have workshops every 2 years. We've had them since 1972. 2 have been in Canada, and we're coming back to Canada next year, August the 2nd to the 8th. So those of you interested in electromagnetic induction, put this down on your calendar. And prior to that date, for 2.5 days, I'm going to be running one of my MT 3D inversion workshops. And these are a bit different. They're not just passive, they're very active, because people have to work in order to be allowed to come to them. They have to calculate the fields and responses for a model that I send people. I also send them the data from a secret model that people have to invert for structure. And this time we're going to be inverting some real data. So those of you interested in trying your MT techniques, please put this in your calendar. But today we're going to talk about natural source electromagnetic methods. And the principal method, 98% of natural source EM is magnetotellurics. But also over the last couple of decades, there's been some encouraging airborne methods that have been developed, and I'm going to be talking about those airborne methods and outlining them very briefly. So we have, in magnetotellurics or natural source EM, we have 2 signal sources at high frequencies above 8 hertz, which is the so-called Schumann resonance. That's the resonance frequency of the waveguide between the Earth and ionosphere. You get energies from global lightning storms. And at low frequencies, below 8 hertz, the energies from solar activity. And as everybody must know, we have an absolutely fabulous solar activity right now. The problem is sometimes it can be too strong, and you can have non-uniform source effects, and you've got to look into your data and take out the non-uniform source effects. But anyway, we've got very, very strong signal at the moment, and likely we'll have it for the next couple of years. We're right at the peak of solar cycle 25. So magnetotellurics in a nutshell, on the left shows the equations. We measure 2 horizontal magnetic fields on the surface of the Earth, and we measure 2 horizontal electric fields and the vertical field, and we relate these together through this magnetotelluric impedance tensor. So the electric fields are related through the MT impedance tensor, and the vertical magnetic field is related to the horizontal magnetic fields. This is all in the frequency domain by the geomagnetic transfer function. And here on your right is an image of me doing broadband and long period work 20 odd years ago in Baffin Island. So in magnetotellurics, we want to measure the electric fields, and we can't. You can't measure the electric fields, but we measure a proxy for the electric fields, and that proxy is the voltage difference between 2 points in the ground. And so we put electrodes in the ground, typically something like 50 meters or 100 meters apart, and notionally north, south, and east, west. And then we put magnetometers, horizontal magnetometers, and a vertical magnetometer in the ground. And these all come back to an acquisition unit, GPS, batteries. So natural source EM has got a number of advantages over controlled source EM. And in Canada, at least, it became very popular to start using magnetotellurics in about the mid-90s onwards. And that's because the companies, the mining companies, they wanted to look deeper. Control source methods is the method to use if you're looking down 300, 400 meters on shield regions, like in South Africa and Canada, because you've got control on the source and you can define your geometry, your source receiver geometry, optimally to image your body. But if you want to go deeper than that, 700 meters or so, you need a much larger source, and logistically it can be very expensive in time and equipment. So natural source EM has got simpler logistics. We're always in the far field. We don't have to worry about being in the near field of the source. If you have a dipole source, eventually at low frequencies, all you'll see is the shape of the source. You won't see anything about the Earth. And you don't have to worry about that in magnetotellurics. We've got very sophisticated data processing and analysis methods now that have been developed since the mid-90s. We have full tensor information, which if you wanted to do that in control source methods, you'd need two sources, orthogonal. We get sufficient distortion removal, and we've got some very well-developed 2D and 3D inversion codes. So the people who are credited with establishing magnetotellurics are initially the Japanese, and they were looking at the relationship between electric and magnetic fields for global studies. They wanted to understand the radial distribution of the conductivity of the Earth. And Hirayama and then Rikitake published papers using the relationship between the electric and magnetic fields. And then Tikhonov published a very short theoretical paper in Russian in 1950. And that didn't have much impact in the West because it was in Russian, of course, and it never really came. But Kenyard, a company, CGG, Compagnie Générale de Geophysique, which is now called Viridian, he's a seismologist working for CGG, and he wanted to look at alternative methods for imaging the Earth besides seismology. And he started looking at these papers of Rikitake and Tikhonov, and he realized that this method would be a potential geophysical mapping tool. And he published this paper, absolutely wonderful paper, and I encourage you all to read it in 1953. And he's the one, in my mind, who established magnetotellurics as a geophysical mapping tool. So in the old days, magnetotellurics was in the universities through the 60s, 70s, and this is an image of the magnetotelluric system that I used in Edinburgh. I'm not in that photograph because this was taken the year before I arrived in Edinburgh. On the right there is my supervisor, Rosemary Hutton, and the second on the left is Dennis Rooney, who was the student, Rosemary's first PhD student, and he took the equipment to Kenya. Lucky guy. And I got the equipment the following year and took it into southern Scotland. And it was just off-the-shelf amplifiers, home-built telluric systems using a design by Trigg from Earth Physics branch in Canada, suspension magnetometers that we bought, and three-component flux gates. The recordings was on a paper chart with colored pens, and then you had to hand digitize the time series. And so here's images from my PhD thesis to show some of the events that I personally, I had to hand digitize 130 events. And so for every site, I had a total of 13 sites. I had all these paper rolls. Went through them and picked out good events. So in a way, it was it was not human intelligence for robust processing, you might say, because I picked out the really nice looking stuff. And in those days, we knew about geomagnetism better than really people who do MT today, I would say, do. And so you could see these different events, and they had the geomagnetic community gives them names. This is the number indicates how long the period is. So these are a PI2, so an instantaneous pulsation. Period 2 is a PC3, so a continuous pulsation at period 3. On the bottom left here, we've got a Bay type event. And on the right there, we've got a PC5 pulsation. And so these were wonderful because you can look at the time series. And I find it a bit sad that nobody looks at time series anymore. And then in those days, the interpretation of your data, and these are the estimates from one particular site, apparent recipient phase, the interpretation was trial and error 1D, and in some cases 2D forward codes. And I didn't want to do that, so I developed a 1D Monte Carlo approach. And you got to remember this was 1977, so computing was rather crude at the time, but I managed to do a Monte Carlo inversion of these data. So modern magnetotelluric practitioners, to my mind, they have an easy life because they've got it all. The absolutely fabulous MT equipment is available now. I'm just showing equipment here from Phoenix Geophysics. And you've got satellite data uploading, 32-bit GPS, so you can sit in your office and you can look at the data that's been recorded by your crew, wherever it is in the world. And we've got some fabulous processing codes that have been developed, most in the late 80s. And then we have some inversion. On the right here are the results from that comparison I did for my magnetotelluric workshop. This is the secret model, and these are slices. On the left is the real model, and on the right are different codes through that inversion of those data. So that our natural magnetic field spectrum, this looks like something like this. And we have three flavors, if you like, of magnetotellurics. We've got the audio magnetotelluric band from 10 hertz to 10 kilohertz, the high frequencies. We always plot with the frequency decreasing to the right because that's increasing penetration into the earth to the right, just like you do in DC resistivity. And then we have broadband magnetotellurics from around 400 hertz to about 10 to the minus 3 hertz. And then we have low frequency magnetotellurics from 0.1 to quite low. And these days, there used to be different sensors for these, but now you get a hybrid sensor that will do AMT and broadband in one. Now, our lining activity is from 8 hertz and up, and our solar activity is from 8 hertz and down. But you'll see these two minima. And these two minima we call the deadband. This minima at around 1 kilohertz. This is our AMT deadband, and this is due to the difference in the source geometry from lightning storms. At low frequencies, from 1 kilohertz down to the Schumann resonance of 8 hertz, the energy is coming to us from cloud to ionosphere energy, whereas the energy that you mostly associate with lightning strokes is cloud to ground. That's coming at us at higher frequencies, 1 kilohertz and above. And there's a natural low between these two types of sources. And that low is too low to make measurements in the daytime. It's too low. It's below sensor noise. And so the way to beat that is with overnight recording. And then we have the AMT deadband, which is the beginning of the solar activity. And that's around 0.1 to 10 hertz. And you can beat that also with overnight recording. I seem to have put some red lines on my slides. I don't know how I managed to do that.
I'm not sure how to take them away. Sorry.
I don't know how to get rid of them either. So please ignore these red lines. I don't know where they come from. So transfer function basic. So here we have the magnetic fields, Hx and Hy, if you like, and electric fields coming out, or a vertical magnetic field. And we want to compute this transfer function, which is our empty impedance. And so these can be described as impulse response functions, and they have zero, or these impulse response functions are causal. And what that means is that at lags less than zero, they're zero. So you've got no output before you got an input. What that means is in the frequency domain that the real and imaginary parts of the transfer functions are related to each other through the Hilbert transform. And on the bottom right here, I'm just showing you the Hilbert transform convolution integral. And this Hilbert transform has got many applications through the sciences. It's also called dispersion relations, Kramer's-Kronig relations, Bode relations, the Kurtz operator, and the Riesz transform. So here we have the Hilbert transform in operation. On the bottom left here, we see the kernel of the Hilbert transform. And so at the frequency you're looking at, it's got no influence on the other part. So if you have the blue here is the imaginary part, chi1. And from the blue, we're predicting, as this filter goes over, we're predicting the real part, which is chi2. And you can see that you get a perfect prediction of the real part. And that's the shape of this Hilbert transform filter. So you can express these now. You can express the impedance as what's called a Schmucker C function. It's just a scaled version of the impedance. And Ulrich Schmucker introduced this, and he likes this because this value C now has got units of distance. And so you can express it in terms of a real and imaginary part in meters or kilometers. And there's a number of inequalities that this C function, which means also the impedance function, must obey. The real imaginary parts of the C function must be greater than zero. The gradient of the real part must be less than zero. And there's quite a few of these. And in the time domain, when we look at our C function in the time domain, we have other inequalities that I list in my 1980 paper, which is the first derivative must be less than zero, the second derivative greater than zero. So these are very, very powerful tests on the constraints of the permitted form of the Earth's impulse response function. But in MT, we know in 1D and in TM mode in 2D that the Hilbert transform is even more strongly constrained, as well as the real and imaginary parts being related to each other through the Hilbert transform. The amplitude and phase are related to each other. And this amplitude and phase relationship is true of any causal linear system that has what's called a minimum phase property. And so in 1996, Bob Parker and John Booker published this wonderful paper on ρ+, and they gave an algorithm for predicting your phase from the resistivity and vice versa. So here on the right, I'm showing you for a particular site, the apparent resistivity in the bars and the prediction of the apparent resistivity based on the phases. And as you can see, we've got some really poor apparent resistivity data exactly in the AMT deadband, but you can predict where it should lie. And so your choice now, when you apply this type of algorithm, this algorithm can identify for you problems. Like these data clearly shouldn't be included in your inversion. This one, it looks like the error bar is too small. So if you want to include that data point, you need to increase the error bar until it comes into the predicted range. And then at the same site, at the low frequencies, what we found for this particular site is that the prediction from the phase, here's the phase on the bottom, the prediction of the apparent resistivity was very good at high frequencies, 10 hertz to a kilohertz, but then the apparent resistivity has dropped off below 10 hertz much, much faster than the prediction. And this tells you there's something going on. There's no modeling code in the world that is going to be able to to match this response. And so if you try to invert those data, your modeling code, they're almost all least squares modeling codes. They work very hard at trying to fit data that are off from the prediction. It'll work very hard to try and fit this data, and it cannot. It can never fit those data. You can do the same in tippers, and this is an algorithm I wrote to test how good the tippers are. So here are the TZX and TZY tippers at a particular site. The black dots are the real part of the tippers, and the open circles are the imaginary part. And I've added to the open circles a range of plus minus 0.02, which is about the range that we believe is appropriate for high quality data. And the blue line is my prediction of the imaginary part from the real part. And so this is a way with tippers that you can actually test whether your tippers are internally consistent with each other. Now you could ask, well, how applicable is this generally? Oh, sorry, before I go into that. One amazing thing that isn't used and should be used much, much more in magnetotellurics, particularly in geomagnetic studies, we know already that we can relate the vertical magnetic field to the horizontal magnetic fields, but less well appreciated is that the anomalous horizontal fields along this profile are related to the vertical magnetic field by the Kurtz operator. And this German scientist, Kurtz, he published this in 1954, this Kurtz operator. You can see it on the right here. And you can get the relationship of HZ, HX from the spatial gradient of HZ. And so this is, these electromagnetic fields, they're not independent. HX, HY, HZ, they're all related to each other and related through this Kurtz operator, which we now know to be the Hilbert transform. And here on the bottom right is an early example of that from Ulrich Schmucker, where he has got the normalized vertical field, and he's taken the Hilbert transform of it to give us this dashed line, and he compares it here with the horizontal field. And you can see the comparison is excellent. So what this means is that you can never ignore the vertical magnetic field. And some people are saying, well, we're only going to model the horizontal fields. But that to me, you're not being true. You're not being faithful to the physics. You've got to model the vertical field. So how valid is this? A couple of wonderful papers published by Zorin in 2020 looked at this, and particularly his 2020B paper. He looked at the validity of the dispersion relationships, and he looked at a data set of over 120,000 MT sites. And he looked at how they obeyed causality, the Hilbert transformation, and he found that less than 0.1% did not obey. So here you can see the total number of sites. So in this case, for this particular geotraverse, almost 8,000 sites, of which 5 were non-causal, 20,000 sites, none were non-causal, 32,000 sites, only 1 was non-causal, 60,000 sites, 6 were non-causal. And so this Hilbert transform relationship, we should be using an awful lot more to validate our data. The other thing you have to worry about in magnetotellurics is called the bias problem. And here we have our estimators of our transfer function. And if we use the magnetic field as our reference, we get this estimator on the right here, which is a downward biased estimator because of the correlated noise. See this auto spectra here. And if we use the electric field as our reference, then we get an upward biased estimator. And so on the right is an image showing this very well from my colleague John Booker and a couple of his colleagues from Argentina. This shows the electric and magnetic used as a reference, a local reference. The upward pointing triangles are the local E field. The downward pointing triangles are the local H field, and the open triangles is XY, and the closed triangles YX. And as you can see, there's very good agreement above about 10 seconds, but below 10 seconds in the empty deadband, at this particular site, the magnetic reference gives you estimates that are far too small. And so as it happens, there was much, much cleaner electric fields at this site. You can get a nice electric field measurement. Okay, in order to beat that, and this is a well-known problem. It was known in economic theory in the 30s and 40s, and a chap called Riersol published a paper on this in 1950, but independently in Magnetotellurics, Gamble and others published a paper called remote reference processing, where he showed that if you've got a measurement from somewhere else that correlates with the signal, here's your input signal and output signal, both have got noise on them, and this is what you're measuring is X and Y. If you've got a measurement from somewhere else, this is your remote reference-based estimate of your transfer function. You'll find that as long as the noises don't correlate with any signal or with each other, they all cancel. And you get the true cross spectra of the remote reference signal plus the input, and the true cross spectra of the remote reference signal and the output. So you get no bias in this estimator. Airborne methods, these have been coming along. The first was ZTEM. It's been almost 20 years now since it was developed by Geotech. And basically, this is a tipper system. So you're measuring the vertical magnetic field in the air, and at a base station, you're measuring the horizontal magnetic fields. And then about 7 years ago, a company called Expert Geophysics started flying what they call the mobile MT system. And that is in this great big bulb here. They have a 3-component coil system inside the bulb, but they don't have any orientation information. And so they have unoriented X, Y, and Z. And then finally, the newest system is being developed by Dias Geophysical, and it uses quantum magnetometers, and they have got orientation. So in this case, you're getting oriented X, Y, and Z in the air, and you're measuring magnetic and electric fields at the base station. So these have a number of advantages, these airborne natural source methods. They're all measuring the spatial variation of the magnetic field, and they're not measuring at all the electric field except at perhaps the base station. So I don't think they should be using the term MT because they're not. But anyway, that's my view. They give you a rapid EM exploration over a large area quickly for a reasonable cost, and they give you a high site density. For example, the ZTEM, a mobile MT, QAMT, they'll make a measurement every 10 to 20 meters on the flight line. Obviously, they're making measurements continuously, but their averaging window is about 2 seconds wide, which is about 10 to 20 meters in time of flight. And the lines are typically 200 meters apart. And you can compare that to what you might do as a high density AMT survey with 500 meter sites. So you've got something like 2 orders of magnitude more sites. You don't have electric field data is the problem. So what are the things to watch out for? One is that most of the anomalous response to a conducting body is in the electric fields, and I'll be showing that. But this is only useful if the EM response from the deposit is in the frequency range of the airborne systems. And these airborne systems typically work from around 20 hertz to about 800 hertz. And then they have a gap in the AMT deadband because they're flying during the day, and you can't make measurements during the day. And some of the systems try to make higher frequency measurements. There's got to be a strong magnetic field response, and I'll show you the response from conducting spheres in a minute. So what I'm going to do, I don't know the technologies of all 3 of those. I don't know enough about the system. I'm going to imagine numerically three perfect systems. The first perfect system, which I'm calling airborne system 1, is only measuring the vertical field in the air and relating it to the horizontal fields at the base station. The second system, airborne system 2, will measure the three components in the air without orientation and relate those to the base station at the horizontal electric fields. And the third system, we're measuring all three components in the air with orientation and relating them to the base station electric and magnetic fields. One thing to keep in mind, though, theoretically, for perfect data, we only need to measure one of these. Let's say HZ, it's easier to measure HZ with a loop. And we can derive the anomalous parts of the horizontal fields from the spatial gradient HZ. So if you have absolutely perfect data, all of these will be exactly the same. So the difference is entirely due to the noise contributions within them. So just a little bit of quick mathematics to show you how we solve for these numerically. We define, when you're doing a numerical computation of the forward response, you have to run two polarizations, source polarizations 1 and 2. So you're relating then the vertical magnetic field to the horizontal magnetic fields times your tippers. And you go through this multiplication, and eventually you'll get your estimate of TZX tipper and TZY tipper from these horizontal, the two different polarizations. It's a little bit more complicated for the airborne system 2, where we don't have orientation. What they want to do, of course, is calculate the relationship between the base station electric fields and the airborne magnetic fields through this admittance tensor. But we don't know the orientation of the bird. And so we cannot derive HX, HY, HZ, but only have the instantaneous directions at any moment in time. We can't take the determinant of A because it's non-square. And so if you have this bird that's being towed behind a helicopter, it's rotating, it's got a yaw, a pitch, and roll angles of alpha, beta, gamma, you can see that what's happening is that your fields are being rotated by this rather complex matrix down here. So there's a lot of rotation of fields into other fields. So what can you do instead? There's a number of different ways. Daniel Sattel proposed in one way to address this is simply to ignore the vertical field. So we're not going to solve for the full admittance tensor. We're only going to solve for the horizontal fields related, the magnetic fields related to the horizontal electric fields. And you can, because it's a 2 by 2, you can take the determinant of it, and it's rotational invariant. And so you get an estimate of conductivity, which I'm calling S for Sattel, given by this determinant here. But note that, as I mentioned before, it's fundamentally incorrect because it doesn't account for vertical field measurements. Another way is called a cross product. And so we're taking the two columns and determining the cross product of the admittance tensor. And then from this, deriving the Froebius norm or Euclidean norm. And the nice thing about this is that it's also rotational invariant. And here's your estimate now of apparent conductivity from this cross product. And another method that I've been looking into is approximate determinants. And this is one from Radich, 1969, where you take your admittance tensor and you deconvolve it into three 2 by 2 tensors. Note that and get the determinant of each of these. So you're approximating the determinant of this, which you can't measure anyway, by this here. But note that, in fact, this very first one is what we just looked at with Sattel. So Sattel ignored these other two. And from this, then you get an estimate, which I call the Radich estimate. The only problem is that I think I've not proven it to myself, but I think this might not be invariant under rotation. Each of these are invariant under rotation, but I'm not sure whether the sum of them is invariant. And then finally, the first order measurement, the simplest measurement. And the simplest measurement that you could make is say, okay, I'm going to just relate the total magnetic field in the air to the total electric field at the base station. And we're going to get estimates of apparent conductivity from this function here. But note that this is a scalar. It's sensitive to source geometry, as I'll show you in a minute, and it's not rotationally invariant. So the final system, this new system from Diaz, which is measuring the electrics and the magnetics at the base and measuring the magnetic fields in the air with full orientation, I think this is the superset, if you like, because from it you can calculate all of the other things. So you can calculate the admittance tensor, you can calculate the full Tipper matrix, and from ZTEM you get the bottom row, but from the Diaz system you get the full Tipper matrix. And you can also calculate the interstation transfer functions. So you can relate the magnetic field at a particular position to the horizontal magnetic field at another position. And I published a paper together with my postdoc a few years ago, just showing the advantages of doing this. So what we want to look at is the anomalous electromagnetic fields in order to understand all these different systems better. Magnetotellurics, Tipper, and the airborne systems. And I'm going to look at two n-member models. The first model I'm going to look at is a 2D contact. And this has the greatest inductive and galvanic effects of all models that you could think of. The second model I'm going to look at is a sphere. And I think, it's not been proven yet, but I think that a sphere is going to give us the smallest inductive and galvanic effects of any model that you can think of. Okay, so here we have a contact, 10 ohm meters against 1,000 ohm meters above a conducting half space in order to attenuate all the fields. And the nice thing about this is that we have analytical solutions published by John Weaver in the 80s. And so we know exactly what the field should look like. And we have two modes of propagation. Is the TE mode, transverse electric mode. That's where the currents are going along the strike of the contact. And then we have the TM mode, where your currents are crossing the contact. So let's have a look first at the TE mode. And this is the electric field and the magnetic field that you would observe at 1 second as you cross the contact from 50 kilometers on one side to 50 kilometers on the other side. And the two different colors are the real and imaginary parts. And here on the left is the electric field in the X direction parallel to the contact. And you can see that we've got a very strong change of 10 orders of an order of magnitude from 5,000 units to 50,000 units. And we need that because the contact itself is 2 orders of magnitude change. So the electric field has to change by 1 order of magnitude because Z is E over H squared. Now, when you look at the magnetic field, what you'll see is the magnetic field source is 1, 0. So at infinite distance, this will come down to 1 and will go to 0. You see the real part, you've got an amplification, you've got a 65% anomaly. It's not as much anomaly as the electric field. The electric field is a factor of 10 anomaly, but the magnetic field has got a 65% anomaly in the real part, much smaller anomaly in the imaginary part. But what you can see is very nice crossover just where the contact is. So this has got excellent localization. Whereas the electric field, it would be hard to say exactly where the contact is. Now, the other mode, the TM mode, this is where currents are crossing the contact. What we have here is a really strange situation. And this is because of what's called Ohm's law. The current density crossing the fault, normal to the fault, has to be continuous. But because the conductivity varies by 2 orders of magnitude, the electric field has to be discontinuous. And so here you can see the electric field changing by a factor of 10 instantaneously at the fault. This slight some strange effects as you get close to the fault. This is due to addition and subtraction of the fields. The other thing that's surprising is that in this mode, the horizontal magnetic fields, these are the magnetic fields that are parallel to the fault, they are totally insensitive to the contact, sorry, not fault, the contact. And this is true of any geometry, of any shape. In the transverse magnetic mode, the horizontal magnetic fields are zero. The anomalous horizontal magnetic fields are zero. All you see is the distant source. So we can construct from that response estimates. And here's the TE and TM response estimates. Apparent resistivity is on the top, phases at the bottom. And in the middle, I've also put estimates from a system called Titan 24, which is a continuous measurement system. And you can see the greatest sensitivity by far is in the TM mode because of this 2 orders of magnitude change in conductivity. We have an order of magnitude change in electrical field. And the phase also shows a very strong response. If we look at what we see from this airborne system, this unoriented airborne system too, of course, it sees the fault, but it's not a sharper response as you get in magnetotellurics. But remember, though, that in the airborne system, we're making measurements every 10 to 20 meters. So we have far more data than we have in the magnetotellurics. So it's possible that when you invert this, you get something close to what you get when you invert the magnetotellurics. And then finally, the vertical magnetic field. So in blue and red here, I'm plotting what the traditional Tipper response. So this is local vertical field over local horizontal field. But then in the ZTEM technique, where you're measuring local magnetic field, vertical magnetic field over distant horizontal magnetic field, you get this orange and green lines. And just look how sharp they are. They're much, much better indicators. And when I've been doing this for 51 years, and I'm still surprised sometimes when I'm beginning to look at fields. You get a much sharper response if you take the local values, and I've put a 0.10 meter sphere down at 750 meters depth, 500 meter radius, in 1,000 meters. And again, we're very fortunate because we have analytical responses from Marc Vallée and Mahomet Masoui. And this is the magnetotelluric response you find directly above the sphere. The maximum phase response is at 500 hertz. Sorry, the apparent resistivity is continuously going down. Why is it not coming back up? Well, that's because you've got inductive effects in these frequencies, but then as you go to lower frequency, you get galvanic charge effects. And these affect only the amplitudes, they don't affect the phases. So here's the electrical field for a north-south source. And you can see a wonderful bullseye, which is about a factor of 2. So we've reduced our electric field by a factor of 2 compared to the background electric field. For the magnetic field, we have a slight increase, and it's about a 10% increase. So as I mentioned before, magnetotellurics, you measure both the electrics and magnetics, but in these airborne methods, you're only measuring the magnetic, so you'll only get a 10% response rather than a factor of 2 response that we saw in the electrics. So here we have the apparent resistivity at 10 hertz, the lowest frequency of measurement, and the phase at 500 hertz. And you can see these wonderful bullseyes. If we look now at the airborne responses, this is the response from only measuring the vertical field in the air, the magnetic field, and relating it to the horizontal magnetic fields. And you've got an anomaly. It's 0 directly on top of the sphere. And this is, if you have a sphere of uniform geometry, you get 0 vertical field right in the middle of it. And as you can see, the vertical field increases as you move away. And we have a value of about 0.06, which is something like 3 times greater than typical noise levels. So we can see this at about 3 times the noise level. For the AS2 system, where we're relating the magnetic fields, 3-component magnetic fields in the air to the horizontal electric fields on the ground, what you can see here is that we've got about a 4% change from the background. And these systems, they typically have about a 4% error. So this one is just on the edge of being seen. If I plot the magnetotelluric response and this airborne response on the same color scale, you can see the difference that the magnetotelluric response at 80 hertz is 0.7 log units, whereas the airborne response is 0.14 log units. So you've got a much, much, much smaller response in the airborne system than you do in a ground-based system. So very quickly now, let's talk about mineral system mapping. And I'm sure a few of you have heard about this. And the idea of mineral system mapping, this emerged in Australia in the mid-90s. And geophysicists are kings and queens in Australia because of the regolith, 200, 300 meters of conducting regolith over bedrock. And so you need geophysics to go through the regolith. Unfortunately, in Canada, we had a glaciation that took the regolith off. So geologists here are kings and queens because they can look at the rocks. So the idea with a mineral system concept, it views ore deposits not as isolated anomalies, but as local manifestations of large-scale dynamic geological systems in which source reservoirs, energy transport processes, pathways, depositional traps, and preservation conditions interact across multiple spatial and temporal scales to concentrate minerals in economically recoverable accumulations. And on the right here is a diagram from Cam McQuaid and John Horonsky, who synthesized a universal process-based framework. So you have at the regional scale, you've got a primary source region. At the camp scale, you have a fluid reservoir. And then at the deposit scale, you've got these fluids coming up through some sort of conduit. Graham Begg showed just how you can map these different scales using different geophysical techniques. And here he defines it in terms of architecture and detection. So for the largest scale, the regional scale, he shows how you get long period magnetotellurics to give you your regional scale. And then your broadband magnetotellurics will give you a camp scale. And then your audio magnetotellurics will give you deposit scale. So let's show this operating. And what I'm going to do, I'm going to take some data from a colleague. These were low frequency sites with about a 10-kilometer spacing on this north-south zone. And my colleague did a 2D inversion of these. And the model that he got out was this, using long period only data. And you can see the site spacing on the top, 10 to 20 kilometers. And he got this conducting blob down about 20, 30 kilometers. So then he went back, and the quality of the data, here's the site directly above the top of that conducting blob. You can see the quality of the data is superb, very good data. So then he went back and he filled in with broadband systems every 2 kilometers using higher frequencies, 460 hertz to 0.01 hertz. And he then did a new 2-dimensional inversion, including all of these. And the model that he got back was this. Now, what you see is this conductor down in the mid to lower cross that goes down into the mantle, and then these 3 fingers that are coming up from that conductor. And the quality of the data, again, is absolutely wonderful. One thing to note is because of the conducting regolith, here we are at AMT frequencies. There's no response at AMT frequencies. So those airborne methods will not be able to image anything in the basement below thick regolith. Of course, that model, if anyone hadn't recognized it, this is the model of an Olympic Dam in Australia, one of the world's classic IOCG deposits. And here is Graham's publication from Nature in 2018, showing these fingers coming up to 3 known zones of mineralization: Olympic Dam, this wonderful C2 coming right up to it, and then 2 areas north and south of it, Vulcan to the north and Werderwell to the south. These are non-economic mineralizations. And so this Olympic Dam was unfortunately not discovered by Magnetotellurics. It was discovered before then using gravity and magnetics by a company, Western Mining, who are looking for buried copper in sedimentary rocks. So its valuation is over $1 trillion. And how many more Olympic dams are out there to be found? Now, on the basis of this figure, this earlier figure from 2008, that convinced the Australians to do large-scale mapping of the whole of Australia as part of the AusLAMP survey. So they've gone and done a mapping at half-degree grid, and they've almost finished it, long period deployments of 4 to 6 weeks. And so they're now getting lithospheric scale structures across the whole of Australia. Following that, Graham went in and did a fill-in on this Vulcan with this grid of broadband sites. And his model from that grid, they knew from drilling, and here's the drill holes, they knew from drilling that there was some conductor below that hit non-economic mineralization. But what's brand new is that Graham found a shallower, much more conducting body to the north. And this is now being assessed for economic feasibility. Another quick example of regional scale mapping I'm taking from Mongolia, from Matthew Como, Michael Becken, and Alexei Kuvshinov. And they did 342 sites across central Mongolia over this Bangya-Hongor Metal Belt. And here's their image, the 3D image, and you can see these lithospheric scale conducting pathways coming to surface. And so the idea of mapping regionally and then focusing in is really important. And then when you've focused in, then you do it at the camp scale. And there's thousands of examples in the magnetotelluric world of this, but unfortunately, most of these are confidential. I've been doing contracting work for 2016, and I've done a lot of projects for a lot of companies, and none of them will allow me to talk about any of the work I've done. And so one of the early examples was the Eastern Deeps. The Voices Bay, this fabulous nickel deposit, was discovered looking for kimberlites, and they discovered the ovoid. And then some TEM mapping found the top of the Eastern Deeps, but then audiomagnetotelluric studies was able to image the Eastern Deeps to depth. Now, there's a whole bunch of these, and I won't go over them, but if you look in the literature, you'll find a lot of examples where audiomagnetotellurics has been used to map or help target mineralization. And here's a list of some of them that you can quickly find in the literature. But as I said, there's thousands of examples that are confidential. So one final thing I want to talk about is reprocessing, reanalysis, remodeling. And a few years ago, a client approached me who was going to spend about $5 million on a drill program based on 15-year-old MT data and a model. So I did some reanalysis and remodeling of that legacy data, and I found some problems with the data. And once I corrected the data, the anomaly in the model went away. And so for a very small outlay, much less than 1% of $5 million, I saved that client $5 million and perhaps a lot of embarrassment. And the same argument for having another pair of eyes. If any of you are doing audio magnetotelluric projects and you have a contractor who's providing you with models, have a second pair of eyes look at that before you go into an extensive and expensive drill program. So where are we going? In general, magnetotellurics hasn't really changed in a couple of decades. We're still doing a lot of single station MT and calculating single station impedances. What we can be doing instead is using a base station to get us a full tipper matrix and calculating the horizontal magnetic field transfer functions. And theoretically, all of these, the impedance matrix, the tipper matrix, the horizontal magnetic field transfer function matrix, they all contain exactly the same information if the data is perfect. And they will all give us the same subsurface. But in reality, because of the presence of noise, all of them will be differently sensitive and have different resolution properties. So all of them, when combined, will improve resolution. And the other thing I didn't get time to talk about, galvanic distortion, but these magnetic methods, the tipper method and the horizontal gradient methods, they're unaffected by galvanic distortion. So instrumentation, we need to get a lot more sensors on the ground. Seismic reflection went through a quantum leap in the 70s when they went from 50-meter geophone spacing to 5-meter geophone spacing. And people doing seismic reflection, they have so much redundancy, they often throw away 80% of their data. But we don't have that redundancy in magnetotellurics. We need to get a lot more sensors in the ground. We need much cheaper equipment. A typical MT system costs about $50,000. We need to get it way down so that you have lots of them. We need to manufacture thousands of systems. We need quicker installation. At the moment, it takes an hour at least to put in an MT site. You need to get them in much quicker than that. One thought is capacitive electrodes at high frequencies, but these only worked about 100 hertz and up. That would save you the bother of having to dig the electric field holes for the lead chloride electrodes. And you don't need to record the magnetics at every site. And one idea I had, this is an image of the lunar magnetotelluric sounder. And here you had a magnetometer. And these 4 balls here, these actually, out of these balls, spring 9-meter cables on the end of which are electrodes. So these things spring out. So why not have some drone-based system that has these, it lands, they spring out, they record overnight, and then they all come back in. We could have hundreds of drones going over an area, recording overnight. Processing, we need to see an improvement in our processing. There was a huge change in our processing in the 80s when we realized how important robust processing was. And here's an example of the processing of exactly the same data using different processing codes. These 3 in blue are the robust processing codes, and those in red are non-robust. And you can just see how much more improvement you get from robust processing. But there's not been a lot of advance since then. What we need is to deal with cultural noise, because it's expanding more and more and more into areas we want to work in, but also we want to work perhaps in brownfield sites close to mines. And here's an example of something I did with my colleague some years ago, where we did the same processing. Here's standard robust processing, and we did wavelet transformation processing. And you can see we did really well using wavelet processing for that particular site, but we didn't carry that on and make it more production. I just wonder, though, whether, given that we have so much data, this might be an ideal issue for AI. I'm I'm not really sure yet about AI. I'm not really sure about it being applied for mineral exploration, because all of our deposits look different from each other. It's very different from seismics, for example, where you have a lot of data and the seismics are flat line structures. It's very different in the magnetic game. So I'm not sure about the role of AI. And then analysis, we need a quantum leap in our analysis of MT and Tipper estimates. We understood galvanic distortion through the 80s, but we need more tools. We need to understand if we have anisotropy in our data. And then modeling and inversion. We've come a long way in a couple of decades. There's a lot of robust 3D inversion codes available. Some of these are free, some of them are commercial, but a lot of these codes, they build the Earth up of isotropic rectilinear blocks or isotropic cells within unstructured meshes. And the Earth doesn't look like that. And the numerical accuracy, the forward solutions of these more and more complex bodies within the surface really asks us to have a suite of control methods. And everything is just too slow and too deterministic. I don't want to walk away from a data set with a model. I want to use a probabilistic approach to walk away with a whole suite of models so that I know what the probability is of various structures. And I think we have to wait, in order to do probabilistic inversion, we probably have to wait for quantum computing to be here, because the 3D forward codes are very slow. So in conclusion, natural source EM methods have significant advantages over control source methods. Magnetotellurics can contribute to exploration for minerals at all scales, from regional to local to camp. Airborne methods can rapidly cover large areas, but they're only useful if the target responds at those frequencies and if the target geometry is sufficient that you get a large anomalous magnetic field. And I didn't have time to show this, but I've done some work where I've inverted these airborne methods with some MT sites, and that really improves subsurface resolution significantly. And finally, there's value in reprocessing, reanalyzing, and remodeling legacy data. So just to acknowledge, very many thanks to SAGA for the invitation to present this. I'm indebted to all of my mentors, all of my peers, all of my colleagues, and all my students in my 50-year career. I've learned something from everyone. I'd like to thank Graham Heinsen for providing me the Olympic Dam example, and I'd like to thank you all for listening to this presentation.
Awesome. Thanks, Alan, for your time, and we, as SAGA, really appreciate it. I don't know if you have a time for a question or two, because I know you have to be off.
Yeah, just maybe just 5 minutes. I do have to dash, unfortunately. I've got another seminar to give downtown Ottawa in just over an hour.
Okay, is there maybe one quick question for Alan? Anyone in the audience?
I'm fully available if you have. I'm going to send this this PowerPoint to SAGA, and anyone who wants it, you can contact SAGA. But also, if you have any questions, just send me an email, and I'm happy to elaborate on anything I've said.
Awesome, thanks, Alan. I see we have one question from Lou.
It's actually Sue.
Hi, Sue.
Sue.
Hi, Sue. Or hi, Alan. I'm sorry I've missed you a couple of times. I just wanted to ask, that one that was on the lunar, is that something that's applicable to Earth systems? I mean, could that be reasonably quickly manufactured?
Oh, I think so. I mean, the problem with magnetotelluric systems is that they're all being manufactured in very expensive countries like Germany and Canada. And there's far more smarts in my iPhone for $1,000 than there is in an MT receiver for $25,000. Yeah. And it's just a question of scale and where they're manufactured. My iPhone's manufactured in China, and they build 1 million iPhones, 1 million cell phones a year. And so if you're building that many, you can make them cheap. You know, if they only built as many cell phones as they build NT systems, there'd be $50,000.
Yeah.
And so, you know, if we were to get manufacturing done in Shenzhen in China instead of in Toronto or in Braunschweig where Metronics is, they'd become much, 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 much cheaper. But with regard to this lunar system, I think you couldn't have normal electrodes on the end of that spring device. You'd have to have capacitive electrodes. And the work I've been doing looking at application of capacitive electrodes, they show very good correlation with grounded non-polarizing electrodes above 100 hertz, but they become much noisier at lower frequencies. I don't know whether this is a fundamental problem in physics or whether it's a technological problem. But it's something worthwhile to be looking into, I think, you know, because the idea of having very cheap devices, drone deployed devices with thousands and thousands of MT sites instead of 40. This makes me salivate just at
Well, we've gotten a